Okay, hello everyone. Today I want to introduce about the shortcuts to adiabatic compression of optical paths in nonlinear Kerr media. And what's the optical soliton? The optical soliton is optical fibers created by the balancing the fibers dispersion and nonlinearity properties. And the soliton can maintain its shape, its velocity, and its amplitude for a long distance propagation. And for its fundamental properties, so we have studied the application of solitons in optical communication, nonlinear optics, and ultra-fast spectroscopy. And for the adiabatic soliton compression, it will require a very long fiber distance. So it may lead to the loss of the coherent. So now we are consider about to use a useful way or method to get the fast and robust soliton compression. Here we proposed the shortcuts to adiabatic for the optical path compression in the linear Kerr media. And for now, there have so many useful ways in these STA techniques, like optimal control, counter-adiabatic driving, and inverse engineering, fast forward, and so on. And for a nonlinear system, like there has no dynamic invariant, so we have proposed a variational approximation approach combined with the inverse engineering for STA design the different parameters in the system. And for analysis the nonlinear Schrödinger equation, then with the variational approximation approach has already effectively applied in the path splitting and the chopped ion transport or something else. And now we focus on our topic about the propagation of optical paths in this system can be described by the following nonlinear Schrödinger equation, and with the variable parameters. This beta is about the group velocity dispersion, and the G is the nonlinear part. The gamma is about the gain or loss. And these three parameters are all vary with the distance. And for convenience, we use the transformation about this wave function, and then the Schrödinger equation can be like this following like this formula, and we make the capital gamma replace the exponent part. And then we can get the Lagrangian density with the initially secant shaped path. And this capital A is about the amplitude. This small a is about the soliton's width. And the B is about the chop. And the phi is the phase. And these four parameters are all vary with distance. And then we can use the Euler-Lagrange formulas to get the generalized Emaco equation. For this equation, we can find it seems to look like a particle. A particle's motion equation then, and the particle has a variable mass, 1 over beta. It's about his mass, and it's located in a variable potential. And from the partial V over partial A equals to 0 gives the minimal point of the potential. From this condition, we can get the adiabatic reference for the Pfizer STA design. And at first, we consider about the system with the constant gain. And then we, from the Emaco equation, can get the adiabatic reference. In order to achieve the soliton compressed from the soliton west compressed from 1 to 0.3, then we need to set some boundary conditions. And the first, second, and third derivative of A equal to AC makes sure that when we design the STA, that the initial and the final state will not have excitation. And we can choose a very simple polynomial ansatz which satisfies those boundary conditions. And for for our inverse engineering with this Emaco equation. Sorry?
This J equals to 7 goes from 0 to 7.
Yeah, this is about the ansatz, the seventh order polynomial ansatz.
Yes, but why it's 7th order?
Okay, because at first I choose about the 5th order. I only use these 6 boundary conditions, and then I find for this ansatz, when I get the ST evolution, the fidelity is not very well. So then I choose more boundary conditions to make sure that the initial and the final state without any excitation.
And is there any physical motivation behind using this triple dot equals to something constant? Because double dot is kind of acceleration, no? If you think of it that way. Then triple dot, there is no what's the triple dot. Like what's the physical motivation of choosing a triple dot equal to some constant? The fourth condition.
It has a name mechanics. The triple.
Sure. What's that?
I don't remember what it's used for. It has something.
Yeah, the idea is that it will make this function more smooth.
Okay, so
We already have not changed in MC yet. That when you meet, that means that you may have function about to become another executive. So the fidelity will decrease. So that introducing more boundary conditions like this will make sure that you don't have no excitations. And the number of boundary conditions will increase. If you have more favorable design,
So this is just at 2 final points, 0 and the final.
Yes, the 0 and the final. Just to combine the initial and the final state will be same.
Okay.
Yeah.
Yeah.
And now we can see in this picture, it's about the red line is about the STA case. We can find it can the soliton width can compress from 1 to 0.3, and the ZF equal to 6. But for the adiabatic evolution, the distance will be longer. But they have the same initial and final state because of the boundary conditions. And then we can redesign the gamma with different distance. The gamma will have the different trajectory. And if the distance is smaller, then we can find the gain, the gamma has a small range about it. The gain becomes to the loss. It's smaller than 0. And for adiabatic and the ST cases, they all have the same initial and the final state. Then we can see the spatial temporal evolution about this soliton compression. We can find for STA case, when the ZF equal to 6, the soliton can be compressed. But we want to know does this compression is robust or enough? So we define the fidelity. This term is about the target state. It's from our adiabatic evolution. And then this term is about what we get from the numerical evolution, use the STA approach. And we can find when the ZF equal to 6, this red line for STA case, the fidelity is almost equal to 1. So it means when we use the STA approach, then we can get the robust and fast soliton compression. And after we redesign the gamma for the soliton compression, now we are focused on the gainless situation with variable group velocity dispersion. We want to redesign the beta. For depression decreasing fiber, there has a different kind of beta, like hyperbolic linear one, Gaussian one, or exponential one. And we compared these 4 different dispersion, and we found the exponential one will, for the adiabatic evolution, for this case, the evolution will be more smooth. So we choose this exponential one. It will decrease from the 1 to 0.3. And for adiabatic evolution, it should be satisfy a condition. It means the dispersion variation pair. Okay, this L is about the fiber length. It means the dispersion variation per length should be very small, should be smaller than 1. So it's the same. At this term, we choose the 5th order polynomial answers because for this case, when we choose this answers, the fidelity it's okay. It's okay enough, and we can find when ZF equal to 6, the red line is about the STA case. We redesign the beta, and compare with the adiabatic one, we can find they all decrease from 1 to 0.3, but they have the different trajectory. And this is about the amplitude for the final state. The red line is about the STA case, and the dashed blue one is about the adiabatic case. They are almost coincide. So then we get its fidelity about the different case, and we found one ZF equal to 6. The ST case, the fidelity is almost 0.99. It's almost equal to 1. But for the adiabatic evolution, it needs more distance to get the Soliton compression. And after we redesign the beta, and we redesign the distributed the gain and the dispersion, we now achieve the Soliton compression. We now think about the Soliton expansion. We already get this replacement in the Schrödinger equation. Then we do some calculation, get the capital gamma's formula. If we want the small gamma is a real function. We make the capital gamma must be greater than 0. So then we can get this inequality. And for the compression of Soliton, the two derivative of A is like this line. And it will be smaller than 0 at the first half distance, like this one. So it means this condition always be satisfied for the short distance when we redesign the ideal gamma. So in this case, this condition is satisfied. But for the expansion case, we can find this blue line is about the two derivative of A. Then we don't know does it satisfied. So we need to find a way to get the rejection about distance. So to adjust this issue, we use the mean value theorem. The mean value theorem is about, okay. Yeah. It's about if we have a function, it's a continuous function located at a closed range AB. Okay, like this one. Then we will always find a point C. At this point, its tangent will be parallel the secant through A and B. We always will find this point. So it means we can find the lower bound about the one and about the first and the second derivative about with the distance. So we can get the CF. And but for this inequality, the ZF is only gives a rough range. So we should like this, when we calculate this formula, we find the ZF should be bigger than 7. But for ST's design, we find when the ZF equal to 7, the fidelity is not very high. It's only about 0.9 or below 0.9. So it means we should choose another more useful way to get to get the lower bound. But this is for the next step, for the next work. Okay, this is about the conclusion, what we done earlier. So, thank you. Any questions?
Sorry, I didn't understand how you define compression.
Compression, okay.
Want to explain how it works?
What you mean how to find the compression?
I mean, your task is compression, right? That's what you want to do.
I mean, I do, okay.
I suppose so. You want to compress something.
Yes, okay, I
have some ideas in my mind what compression means.
okay, the compression means like we have a path and we have its width, like at first it's equal to 1, like this width compression, and then after a propagation distance, it will become more thin. The path will become more thin, like the width becomes smaller. So it means this path be compressed. And just look like this. At first, like its width like this, and then
So you have just like a wave.
wave,
Like a function.
like a function.
Like this u is a wave.
This u, yeah, it's a wave. Yeah, it's this u also we can like the wave function, the cosine. It's the same. It's the same.
So you can think about it like a regular wave, like you have this u as a function of t, z for instance, and you fix some t, then you have some function. Right. Like for instance, like you can have something like this. And then you fix some t.
Yeah, I give a range about the t because it's the.
And then you have some function. So this is a wave, right? So this is sine. For instance. So what do you want to do with this function?
Okay, I know. Okay, in my case, I choose the initial state as I choose one initial state is like a hyperbolic secant function. It's about more looks like a Gaussian one.
Can you define this or make a drawing?
I think
you can remove your mic.
Okay, I think I have plotted this amplitude. I think it's okay. Look,
this is your function.
Yeah, this is my function. This is my initial state, which I choose for the I choose the second one.
It's a wave function like in quantum mechanics. It's a complex thing.
Yeah, same. And this function okay, remove. I choose this at t equal to 0 like. Okay, this is my initial wave function, and I put it into the Schrödinger equation.
Okay, so this is a function of z.
Yeah, it's a function of z. Sorry.
And t as well. T is fixed.
This is about the temporal.
Okay, what I said. So you basically have like differential equation which defines.
Sorry.
I don't understand the problem. What is the problem? What are you defining?
Okay, like we put this initial state into the nonlinear Schrodinger equation and then control some parameters from this equation, then to make this initial state change into the like this amplitude change into this way, this shape.
So you have a quantum system described in an initial quantum state. Then you perform some evolution. And the compression is the evolution that leads your initial quantum state towards this one in the picture. That's what you want to do.
Okay, like this way.
I mean,
Yes.
I'm asking, just stating the definition.
Okay, I think okay.
I mean, that t variable, what does it mean? It's the time, or it's a spatial variable?
This soliton is about a temporal soliton, so it will be expansion or compression in the t axis, and it will be propagation in the z axis. So it will like a 3D evolution.
But then it's a spatial variable, no? It's not temporal variable, it's not time, or yes?
It's not.
Should be done.
I know something really well this.
Yeah, it's a good question.
Like I understand you have a wave traveling through a
Distance, yeah, probably.
like through a cable, for example, or through a well, it's not a cable, it's an optical fiber.
Yeah.
It's like a tube. So
Yeah.
you have this set axis,
Yeah,
then you have time because the wave
exactly.
evolves, and t is the time, or is the width?
T is the time. But yeah, T is the time, and
So you want to compress it.
I want to compress the soliton in the distance
So you have to design a function for the distance so that it compresses in time.
Compresses time.
Not compresses time, compresses in time, the wave packet. So you start with you have a tube, then you have to.
Well, but if it is a traveling wave, to compress it in time is to compress it in space also.
Yeah. You mean
If it is traveling, like having a quicker, like on and off of the signal, is to have like a wave packet that is smaller in distance also, right?
Yeah, but would it be robust?
Huh?
Would it be robust to do that? Just switching on and off?
It's like a simple case. I'm not saying that's the good way to do it, but so can you please put the previous slide?
you mean the amplitude?
The one with the compression, that one, yes.
You mean this one?
So that is at the beginning of the optical fiber, or at the end of the optical fiber. That is the signal that is passing. U is the signal that is passing.
Let's see. The U is about the amplitude.
So if I'm understanding correctly, is at the beginning you have a very wide pulse,
Yeah.
and at the end of the optical fiber, the pulse has gone this.
Yeah.
Yes.
Okay.
Okay, sorry. Yes, this blue line is about the adiabatic evolution after the long distance it can from this way to the It's the same
So
one.
the compression is how much, like this width divided by this width.
Yeah, from this picture, we just compress. We can use the soliton's width to define the compression. Like I always said, we compress the soliton width from the 1 to 0.3. It means the soliton compressed.
Okay. So this D should be thickness, not time.
The T is the time because it's because this soliton will be expansion in time axis. Yeah.
This
In this picture, it should not be time.
exactly. In this picture, it's the soliton at final and initial times. So initial time is given by dotted, and final time is the red curve.
Initial state and final state, you refer to the beginning at the end of the optical fiber.
Yeah.
So this D should be thickness. I don't know.
No, it can be time because it's like the first, like the. Imagine that wave is coming like through out of the cable or out of the
Okay,
fiber,
just like.
and then it starts giving signal, and then it goes out the signal. So at this first X point, if you have like a GIF or an animation, you can have time also.
Okay, this is about the evolution. System distance. This is about the time axis, and this is the initial state. This is the final state. This is for the STA design for the evolution.
But I was confused because you used initial state and final state to refer to like the beginning of the fiber and the end of the fiber. So I understand that it's a packet traveling, so it's also the initial time and the end time, but then in the x-axis you use time also as a variable. So I wasn't understanding how you would have the initial, like at the beginning of the time, and then also have time as a variable.
Yeah.
That's what I was confused by.
But now you understand the thing.
Yes, I understand that it's
Because I don't understand anything. For instance, like let's say I fix some instant of time
Instant of
for
time.
this wave function.
Yes.
At the beginning of this plot, like the left side, it's roughly 0. If I fix some time there, which is roughly 0, then I ask for the probability of my, I don't want to say particle,
And
particle being found in some z. It doesn't matter the z, it's 0 the probability. So my particle is not there. And a wave function needs to be normalized, right?
This function.
How do you
This is normalized.
This is already normalized.
But it's normalized for each of the slices of the time.
Yeah, but
Yeah.
The time is no way when I normalize.
let's say I fix some time. -5. Then I integrate over z. It should be equal to 1.
Can I this? Are you sure this T is time? This is thickness. I think it's still
I don't know.
thickness.
I don't know.
I mean, because this soliton is the temporal soliton. It has the distance and the time control this soliton, and we also have the spatial soliton. Spatial. At this axis it will be x. It's the different kind of solitons.
Yes.
And so it means when. Okay, how can I say?
So time is an observable
The time is the.
in this case.
In this case, what?
Is it or not?
But
Like in regular quantum mechanics, time is not an observable. Do I agree?
But this T is for solving the differential equation.
Because I don't understand like this wave function. Why is it not normalized, for instance?
But Mateus, I think that this is for representing what the evolution is. It's not the actual thing that you are doing, because what you're representing here, T equals 0, is the middle of the soliton. No?
T equal to 0.
Yeah. So the time at which the middle point or the maximum
amplitude of the probability distribution for the soliton passing each position in the K1, in the optical fiber.
Optical fiber.
Because otherwise it's very difficult to represent four-dimensional things in 3D, I guess.
That 3D picture is the heat map you put in your presentation. There's that picture that is seen from above like a heat map.
Yeah, it's the same. So
How do you define normalization for this wave function?
how do I design the process? How do I design the
Normalization.
normalization? It's normalized.
Should be a bit set, because like, this is just a representation, so I wouldn't worry so much about this. Because here you mix everything, but it's like how do you define soliton passing at set equals 6, and then you want to see how the evolution is, because also obviously the propagation of the wave is in the same axis, so it's a little bit strange to do this kind of thing, but
Okay, so the observable is t, not c.
no, but this is not just a it's just a variable such that you can give some nice plot.
Exactly, it's not an observable, it's just some variable so that you can give a nice plot, that's it. It's not an observable, I think. But I still get what t equal to negative value means.
No, I guess because it's that the soliton passing at 0.7 or 0.6,
0.6?
then you define the maximum of the probability because this wave packet is symmetric, so that you can define a middle point. And then at the time the middle point passes through this point, you define t equals 0 at set equal whatever.
Oh. So you
Then
this is just a choice of.
Yeah, then the normalization you have to just slide this in the like this.
In time.
Yes.
Yes,
Or
yes.
in set.
In set.
In set.
Exactly, yes. You have to slice it in Z, and one of the graphs that she was showing was the last Z, right?
Yeah.
Last Z and the first Z.
Yes.
Both of
Initial
them.
and the final.
Okay, slide in everything, yeah.
I think it's a nice plot because you can show everything with just one plot. So.
But what's strange for me, I think because I don't know anything about solitons and I want to understand. This is not like a critique or something. It's generally because I'm not understanding. Imagine you are in the middle of, please read the graph. Imagine you are in the middle, in set equals 3, and you are standing there. And if you move through time, suddenly a wave appears and a wave goes. No? I don't understand that wave, where does it come from? It comes from other sets, but from other sets and other times. No? So shouldn't like that tube be diagonal?
But this is like if you are starting at set equal 3, you start not looking, not receiving any amplitude.
Yes.
Then suddenly you receive an amplitude in one dimension.
Yes, you receive the amplitude and then the wave passes you and
Yeah,
you
and
stop.
then you have all the information about the amplitude that you have received. And then you define, okay, which is t equals 0 at this point. T equals 0 is the maximum amplitude that I have.
Okay, so instead of t is like the t where the maximum has happened for this point. But if you have a regular t, you can have that same graph, but with the tube instead of t equals 0 at a level.
Yeah, if you put a GIF here, if you do a 3D plot with, or a 2D plot with a time machine that what you would see is the solid moving and compressing. Yeah, you cannot do this in PDFs and stuff.
But I mean, but you can do it diagonally with the T for an outside observer. Instead of the T, because that T variable
Yes,
is
you
defined
can
differently
do
for
it
each
diagonal.
one.
Yes, you can do it one. It's a choice. Does this plot look nice? Yes, there is a nice choice.
Okay.
Yeah, because the other thing is would be straight, like white diagonal.
That way you are defining T differently for different values of
Position.
zeta. So
Yeah.
T is really a function of zeta, of Z, sorry.
In this, I only want to get the
Now I believe I understand.
difference. You see.
No, this is, I believe this is basically because I don't know about Soliton, so this like kind of way of representing things, I'm not used to it. So that's why I wasn't understanding.
Oh, yeah, but Soliton is family noise.
I would work with them, and this is, it's, for me, it's a strange choice of how to present it, but it's for me. I don't know.
Because then in the other way, you said that you have to still define a t equals 0.
Yes. The t equals 0 is when the wave packet
One T
is
equals
at the
0.
beginning of the cable.
And what is that? What is the wave package being at the beginning of
The maximum of the wave, like you can define where the packet is, because you can define where the maximum of the packet is.
Okay, so it's just a way of representing it.
But for me, if I see that graph or that plot, for me is that for an outside, that T for me is the time of an outside observer. So I'm watching a cable and suddenly the whole cable receives a signal and the signal goes off.
Yeah, this in the paper is solved by reading the caption.
Yeah.
So I didn't worry too much about this. Yes.
Which is, if you, with an explanation, I understand.